Today we're going to look at serial bus, one of the serial buses, universal serial bus, or USB. We're going to talk about some basics. We're going to look into what is a USB transfer, types of transfer, and how do we make choices on controller chips. So let's say you want to have a very good peripheral interface, which is fast, reliable, versatile, inexpensive, and conserving power, supported by different kinds of operating systems, easy to use, no need of details on configure or setup, and you end up with an USB or universal serial bus because it has all these nice features we would like to have in a peripheral device. It's very easy of use, one interface for many. It's easy to connect. Cable is easy, it's hard pluggable, and sometimes no external power supply is required. Well, most of the time, unless you are trying to drive a very power-hungry device. For example, maybe RF transmitter that you need to supply external power. It can support different speeds. With USB 2.0, it supports 480 megabits per second. In newest USB 3.0, it supports up to 4.8 gigabits per second. It's very reliable. In most of the USB devices, or the controllers, low cost, consumes low power consumption. And it's very good for developers because you can design a device that hopefully will work with many of the different platforms. There are also some limitations. For example, speed and distance. 4.8 gigabits per second for 3.0 it's good, but it may not be satisfactory for some applications if you want to transfer a larger amount of data. It also has limits on the distance of the cable. For the peer-to-peer communication, it supports host to peripheral only. You cannot do host to host or peripheral to peripheral. That means you essentially have a master or host device, host controller, and then peripheral devices. You cannot do broadcasting. The protocol, USB protocol itself is in fact quite complex. You need to spend time to understand the exact format of the messages. For new operating systems, you may need to design device drivers. Also, if you want to have a vendor ID, like the PCI vendor ID, USB and vendor ID is also not free. You can connect USB peripheral devices to a host controller or USB hub in many different ways. Here are some examples. You can have a root hub in the motherboard, which goes off to another hub, and you can connect different devices. You can even chain these hubs to expand the number of devices you want to connect. And these are some other ways you can expand the number of connections. So we know that for USB communication, we need a host side and device side. For host side controller or hardware, you need to have a USB host controller and root hub plus some operating system support. The responsibility of this host side USB controller is to detect devices. So when you plug in a new USB device, the hardware and the OS should be able to recognize the device, whether it's a webcam or it is a USB thumb drive. It will manage the data flow. It will have to do error checking and provide power for the device. It will handle the data exchange between the host system and peripheral. On the other hand, on the device side, You will need to have, again, a USB controller plus necessary hardware or firmware. You will need to detect communications to the chip. And device has to be able to respond to standard requests that are coming from the host side. For example, the request could be for vendor ID, status, etc. It will also need to do error checking. It will manage power and exchange data with the host. So let's say we want to develop a USB device. Here are some of the main elements you need to have. You need to have a controller chip with a USB interface. Because the complexity of the USB protocol, it's not feasible for you to design from scratch. You do not want to write a firmware of your microcontroller to handle all the possibilities of USB messages. Instead, you need a controller, a USB controller that's capable of doing this work. With that, you can write code in your peripheral device to carry out USB communications. Of course, you need other hardware or software for the peripheral. If it is a thumb drive, you need to have flash memory. If you want to have a USB popcorn maker, then you have to have a popcorn maker. On the host side, you need to have a motherboard and operating system that support USB. And that means you need to have corresponding device drivers on the host. Fortunately, many of the modern operating systems do have a large number of device drivers for different kinds of USB devices. You may need to do customized application design on the host for your particular USB device. For tools and steps, you need to have assembler or compiler to create device firmware on the device side. You need probably a device programmer or development kit. PIC18 is example. You need to have programming language and SDK for host side software development. You need to have a monitor program for debugging, and most importantly, it will be very helpful if you have a protocol analyzer to view the device the USB traffic over the USB bus. There are certain steps you need to take. You want to do some initial research to make your initial decisions on what kind of controller you need to use and what kind of programming environment you want to use. And you want to implement some of the key communication. For example, enumerating, which essentially refers to how you want your device to be recognized. And the last step will be the actual exchanging data between your host and device. Initial decisions include you want to understand what's the requirement of your USB device, how much data you want to store or transfer, and how fast you want to transfer these data. What type of error checking mechanisms you want to employ. You want to do CRC or you want to do other error checking methods. And power limit. Power limit is important. You want to figure out what will be the power draw of your device. If it's a popcorn maker, certainly it will be much larger than the thumb drive. But how much? And that will influence on whether you need to have an external power source for your device. And any other functions that you may want to include in your device. Drivers. We're talking about software drivers. If you design a device that's of a standard category, for example, if you have a new keyboard type of USB device or new thumb drive, these are well-known devices. You may not need a new driver on the host side. But if you are designing a very new type of device, which is different from a keyboard, different from a flash drive, different from the existing devices recognized by the host, then you need to think about how you design your customized driver. And of course, for all this, you want to select a controller chip that can meet your requirement in terms of the design tools and languages. Enumerating is basically you want to be able to present your device to the host as a known device. You will need to have firmware code on your device side for your controller, and this particular controller chip will send descriptors to the host following the USB communication protocol. Descriptors are in fact the information about the capability of your device and how to use your device. And chips must decode and respond to host request. When you plug in a thumb drive into the USB slot of your computer, actually the root hub and the host drivers send a bunch of USB requests to the device. It asks about the vendor, asks about the capability, asks about the capacity. All these things, questions come in the form of request. And your chip, your USB controller chip on the device side has to respond to these requests. For Windows, there are INF files for devices, and these INF files contains information about the device. You may need to have debug circuit or development kit for testing the chip, and you want to test out whether Windows can enumerate the device. And you want to repeat the steps if you have multiple endpoints that present on the device. So for example, if you have a USB 3G dongle that you use to connect your laptop to, let's say, Verizon's 3G network, when you plug in that 3G modem, it actually presents itself as two devices. One is the network device. The other one is actually a thumb drive. And the thumb drive often contains the setup files that you need to install the applications and drivers to the host. And the network device itself is responsible for the actual communication. So this enumerating process may take several iterations. It's simply because the device you connect may have multiple functions. Exchanging data. After enumerating, the code to test data transfer has to be designed. You probably will need to write application code for non-standard devices. What's happening during the data transfer is in fact the exchange of USB messages. Include communication for enumerating the device, also communication for application and device purposes. So at the very beginning, it's kind of the host driver and device trying to negotiate to find out what type of device it is. And after enumerating is done, so the host is able to recognize the device, then the actual communication is going to happen. I mean, the data communication is going to happen. In the enumeration communication procedure, the host will send out requests and the device will respond to these requests. For Windows, you need an INF file to identify the file name and location of the device driver. For Linux, it's a different method. Device driver will present, and also we require the firmware on the device side is functional. All this happens is invisible to the user or to the application. So the end effect is that, let's say if you have a USB to RS-232 converter, once you plug that in, your Windows or Linux operating system will recognize that as a serial port, either COM0 or COM4, depending on the number it's assigned. Then for your upper layer user applications, you just open that COM port. It doesn't really know, in fact, underneath the USB communication is happening. For the application, it uses OS APIs. It can read or write from the device. For the device side, it will put data in the USB controller's transmit buffer, and on the other direction, it will receive data from the receive buffer. And most devices need firmware to support error checking and error handling. In terms of USB transfer types, there are 4 transfer types: control, interrupt, bulk, and asynchronous. Physically, there are 2 signal lines on the USB bus, and that's why it's called a 0. These 2 lines, D plus and D minus, carries a differential signal. Conceptually, these 2 lines will carry frames and microframes. As we see here, we have 3 frames. Each one is going to be transferred with 1 millisecond. In one frame, you can see that we have a start of the frame flag and followed by different transfers. And what we see here is device 1, endpoint 2, device 2, endpoint 2, etc. We'll see shortly that device ID and endpoint ID is the way to identify the communication endpoints. At low and full speed, the host will schedule transactions within 1 millisecond frames. At higher speed, this frame is going to be shorter. It'll be 125 microsecond frames at high speed. We said that each transfer, each frame consists of 1 or more transactions. And control transfer always has multiple transactions. So in order to enumerate a device, there will be a lot of control messages, control transfers happening ahead of time, ahead of the data transfers. Other transfers may have too much data to fit in one frame. In that case, it will go into different frames. Each transaction must include device address and endpoint information. And that's the one we saw. We have device ID and endpoint ID. So what is the endpoint? Endpoint, by definition, is a uniquely addressable portion of a USB device that is the source or sink of information in a communication flow between the host and device. So on one side, we know that that's the host, that's the root hub, that's the host device USB driver. And all the USB devices are going to communicate with that host. So on the device side, as we explained earlier, one device may have multiple functions, so multiple endpoints. So we're going to use these as an identifier of the communication pair. We know on one side is the host, but what's on the other side? What's on our device side? We use this uniquely addressable portion to identify that. And the communication could be either into the host or coming out of the host. So endpoint also has this information, this data transfer direction. All traffic travels to or from a device endpoint. Endpoint is a buffer storing bytes, because the reason you have a USB device is to do some kind of communication, and you want to have a buffer to either do the transmitting or do the receiving. And endpoint is the unit to do that. Data stored at endpoint may be received data or data to be transmitted. Endpoint address has endpoint numbers and direction. up to 16 endpoints can be specified, and you can have either in or out on any of these endpoint numbers. One special endpoint is the endpoint 0, which is the control endpoint. It has both in and out directions. A full-speed device may have more endpoint addresses. Transaction. Every transaction begins with a packet that contains endpoint number and a code that indicates either the direction of the data flow or whether or not it is initiating a control transfer. So we have this table that lists some of the transaction types. We can have in, so that's going to be from the device to the host, and you can have different kinds of, you can have data or status information going this way. For out type, you can have, this is coming from the host, and you can do data or status. For setup, it's from the host, and that's for control only. And that's essentially a request coming from the host to do the enumeration. So pipe is the logic data flow. It's an association between device endpoint to the host controller software. And it's established during the enumeration process. For control pipe, that's the one we use to relay control information, control data, control packets, and that uses endpoint 0. Endpoint descriptor received by the host, one descriptor for each endpoint, and this descriptor has information such as the addresses, types of transfer, max data size, and desired data transfer interval. Okay, this table has a lot of information. It essentially explains the transfer types: control, bulk, interrupt, asynchronous, synchronous, and these different transfer types are for different usage. For example, for control, it's mainly for identification and configuration, and this asynchronous is for streaming of audio or video, and they have different properties on the speed and data size and the directions, what kind of error checking is employed, etc. I will not go into a lot of details. Okay, so a transfer is made of multiple transactions, and transactions is made of multiple packets, and these packets may contain the endpoint ID, the addresses, error checking code, or the actual data. So this is kind of the logical structure of these different building elements of for USB communication. To ensure the success of a transfer, you will need to do a lot of handshaking. Essentially, the endpoints of a pipe should do this handshaking to do acknowledgement. If the data transfer is successful, you will acknowledge to the other side. Otherwise, you give a negative acknowledgement to indicate the device is busy or there's no data. There are also other messages you may use in the handshaking process. For example, star to indicate it's not a supported request, not yet to indicate it's data is not ready, and error, it specifically indicate what kind of error it is. Okay, so we know there are a lot of details in USB transfer, and we really do not want to reinvent the wheel to implement all the transactions or all the control signals. There are a lot of microprocessors with USB controllers that you can leverage. Because there are so many such controllers, to select a good one is an important design decision you need to make at early stage. There are different kinds of criteria of selecting such a controller chip. For example, function, cost, availability, and also ease of development, which includes whether you have well-supported development tools and example code, and what languages example code uses, etc. The device, we said that we need to implement the USB protocol. It needs to respond to the request coming from the host. It will need to receive and transmit data. For USB controller chips, some only require accessing registers. You can implement USB functions. Well, some require device firmware to handle details. And some controller chips have a general purpose CPU, and you can offload some of the work to the general purpose CPU. And some needs external ones for non-USB tasks. You do have options to use ASICs if you have design that will not be changed later. So USB ASICs is also an option. A USB controller contains the transceiver, which handles the low-level signaling. It's the hardware interface between USB connector and the controller circuit. It also has a serial interface engine, which is used to handle sending and receiving data. In addition, buffers are often included so that you can temporarily store the received data or the data to be sent out. Because you are talking about high-speed transfers, the speed can go up to 480 megabits per second or even 4.8 gigabits per second for USB 3.0. So the buffers are important to handle the data transfer spikes. And you need registers for configuration, status, and control, etc. And clock is usually provided as a part of the USB controller. Other components you may need on the USB device, other processors. If you have this USB controller as a part of the processor, then you will need to decide what are the functions you want to put on the major CPU. You may need program memory, ROM, EEPROM, etc. Data memory is probably needed as well. You may need other I/O interfaces depending on your application. You may have the need of RS-232 or I2C, or you need AEC to do some analog to digital conversion. To select a chip, it's recommended that you select the familiar chip architecture and the programming language. For example, if you learn a lot from this class, you will probably getting very familiar with PIC microcontroller. PIC does have a lot of microcontrollers. Microchip has a lot of PIC chips with USB controllers. You need detailed and well-organized hardware documentation and sample code. And of course, you need a easy-to-use development tool, SDK. Here's a table that gives you some examples. For example, from Atmel, it has chips that support full USB speed. And you have Intel's microcontrollers here that supports full speed or high speed. Microchip has this PIC18F4550. This is a very popular USB controller that you can use, and there are source code examples that you can leverage to speed up the design. This is the little detail regarding to that chip. It supports low and full speed. It has a flash-based program memory with 256 bytes of EEPROM. It can support a bootloader. Bootloader is a special program that resides in the microcontroller. With this bootloader, you can load new application firmware without using a flash programmer. So essentially, inside the chip, normally you have your application firmware like you design in your lab 2 and 3. You can just program the chip using the PIC tool. Okay? Without the PIC tool, how do you update the programs, the firmware in the microcontroller? Bootloader is specifically for that purpose. So with the bootloader, if you can have, for example, RS-232 interface to your chip, to that microcontroller, you can set the chip to operate in the bootloader mode. And in that mode, new application firmware can be uploaded to the chip through the RS-232 interface, and bootloader will write the new code. We're talking about application code to a specific section inside the microcontroller. So inside microcontroller, you essentially have 2 segments of code: the bootloader itself and an application code. This code, this bootloader, stays there all the time. With this piece of code, you can update this segment of your code without using a programmer tool. So that's the main purpose of bootloader, which is very helpful if you want to upload or update the firmware after the chip is deployed. This chip also has other interfaces, UART, I2C. For USB, it supports all 4 controller transfer types. It supports up to 30 endpoint addresses, and it includes 1 kilobyte of buffer memory.